continuing my series on Python for physics people. Those physics people could be instructors. They could be undergraduate students. I feel like I say the same thing every time, but maybe you haven't seen my previous videos, so I'd like to give you a little introduction. I'm working through some things that I could do in class that you could then use to implement and use Python in your physics class. And maybe you're an instructor and you want to do this, then you use this stuff. Or maybe you're a student and you're trying to learn it on your own, then use this stuff. Okay, so I've worked through the first semester of introductory physics, calculus-based physics at the college level. That's my primary aim at this point. And now I'm in the second semester. We're doing electricity and magnetism and electric fields. And here's something that I want to do. So a lot of times in the textbook, they'll say, okay, look, if you could have a solid sphere, insulating sphere with charge uniformly throughout the whole thing. You could have a metal sphere with charges on the surface. But in both cases, if I am some distance r from the center of that, the electric field would be the same if they have the same charge. So let's say this is r, and we could just say that's the same thing as the magnitude of that field would be E equals 1 over 4 pi epsilon naught q over r squared, where that's the distance from the center. Okay. So you're like, okay, fine, I believe you. It just makes sense. It's spherically distributed, but I'm not really sure. But what can I do? I'm just a student. I can't figure this stuff out myself. Or how can we show this? And there are ways to show this, but I want to show it my own way. And so what I'm going to do, hopefully, I haven't worked this out beforehand, so it should work, but it could be a disaster. It could go down in flames. Who knows? The idea is to make a Monte Carlo calculation of this sphere and then of this sphere. Okay, so let's do this one first. And so what I'm going to do is I'm going to make, let's say, n equals 1,000 points, uniformly distributed throughout a spherical surface. And then I'm going to calculate the electric field due to all those, where each of those points will have dq equals q over n charge. So I need to know the location of each charge, and I want to know the location of my observation location. I'll call that RO. And so with that, for each electric field, I can say dE, the electric field due to each individual point, is a vector, 1 over 4 pi epsilon naught, dq, the charge of each one, over r magnitude squared, r hat. And so r is going to be RO, the observation location, minus RQ, the vector location of each charge, because the charges are all in different locations. So I'm gonna number one, make 1,000 points, and 1,000 points of light. Oh, I'm sorry, points of charge. And so this, I'm going to use the random function. So let's pick some things here. Let's say Q equals 3 times 10 to the negative ninth, negative 6. I'm going to go with negative 6 coulombs. R, the radius of my sphere is, I don't know, a centimeter. R equals 0.01. And then N is 1,000. So I need to generate 1,000 points, and I'm going to display them just so you can see what they look like. But other than that, I'm just going to use, I'm just going to calculate the location. I'm not going to, yeah. And then so that's it. I'm going to go through, make 1,000 points for each one, calculate the electric field to each one as I calculate it, as I make it, add it to my total electric field, and then I'll get a sum. And then at the end, I can compare that to this equation and see if they're the same thing. Now, if I'm really doing great and things aren't going well, I could actually make this as a function and then change this as the distance of r. But if I just show it at one point, some arbitrary point, that should be a good enough example. And then after that, I can do a shell and show that these two have the same electric fields. Let's get started. Jumping over to Python. Gonna get started. Here we go. Python. Okay. So, ooh, that's weird. Okay, so this is Trinket GlowScript v Python. I've already started. This is my. I made this. Oops. I made this last time. This is my function to calculate the electric field. So if I give it the location of the charge, the location of the observation location, and the value of the charge, then it returns the electric field. So, but the first thing I want to do is let's start and jump in here and make our charge stuff. So I'm going to say Q equals, what did I say, 3 times 10 to the negative 6. R equals 0.01. and n equals 1,000. Let's start with 100. It's always best to start small, right? Because if you make a mistake and it's big, you make a big mistake. But if you start small and you make a mistake, it's a small mistake. You can always make it bigger. Okay, so what I want to do is to say, this way I like to do it. N equals 0. That's my counter. I'm going to count up to n. I need dq equals q divided by n. And then I'm just going to say, while n less than n, let's just do this. N equals n plus 1, print, and just to show you how it works and to test for myself how it works. And it goes up to 100. So I made one too many, right? Because I made 100, it goes up to 100, but it started at 0. No, it didn't, because it said I added. See, I always get confused whether I have one too many or not. But you know what? When I get to 1,000, not going to matter. 1,000, 1,001, no difference. So I'm just going to not worry about that right now. You can worry about that on your own time. I don't want to print that. What I want to do is to generate a random vector. So I'm going to call this RT is equal to R times vector 2 minus random 2 minus random. Is that right? So random goes from 0 to 1. So it's 1 minus 2 random. 1 minus 2 times random. So random could be from 1 to 0. So the maximum this could be would be a random number of 1. So 1 minus 2 is negative 1. The lowest it could be is 0. 0 minus 1 minus 0 is 1. So it will go to between... Oh no, I want it to go... I don't want it to go... Yeah, I do. I'm going to make a box. I'm making a box of numbers, right? In order to make a sphere, I'm going to make a cube that has a size of 2r. And then I'm going to cut out all the things that aren't in the sphere. So I'm first just going to make a box. So that's my x component. My y component is going to be the same thing. And my z component. That's my... I'm just made it as a vector. Now let's draw a sphere with that location. This is going to be a box, like I said, because so I'm going to say sphere. I'm not even going to give it a name. Position equals RT. Radius equals, let's say, R divided by 100. I'm just not going to worry about that. Okay, let's run that. And that looks pretty nice. There's my box of 100 points. Let's make the points a little bit bigger. R divided by 50. That's 100 points in a box. That's a cube. You can see that's a cube. If I increase to 1,000, you can see that's really a cube. See, that's a cube. And that's pretty cool right there, right? I can zoom through it, zoom back out. Okay. So now what I want to do is to cut out all those pieces that aren't inside of the sphere. So if I do this, I have my random variable. I'm not going to draw the sphere unless I'll say if mag RT is less than or equal to R, right? If that's true, if it's less than the radius of the circle, then it's in the sphere and I'm going to make it. So I'm going to just indent this and indent this. So if I'm not going to count it unless it's in the sphere. So if it's too large, I'm just not going to draw it. Let's see what that looks like. There's my sphere, see? So it's like that whole thing. How do you sculpt stuff? Well, you take a block of marble and you cut away everything that's not what you want to sculpt. That's what we did. We cut away the stuff we didn't want it. And now we have, that's 1,000 random points. That's it. That wasn't too hard. Okay, so now I need to, let's pick my observation location. So I'm going to say RO equals vector. It's on the x-axis. Let's say 2 times R, 0, 0. So it's just twice the radius away. That should be fine. Now I'm going to say, this is not going to be hard. E equals vector 0, 0, 0. So what this does is I'm going to calculate the electric field due to each of those pieces that I create at the location R0. And so then I'm going to add it to my total. So I need a total starting at 0. So I can add it to it. So down here, I'm just going to say, if I draw a sphere, which I'm going to leave drawing it in there, then I'm also going to calculate the electric field. So I already know the location of that sphere is true. Its location is RT. So I can say E equals E plus, Oh, made a mistake. So I'm calling this function e up here, and I'm using e down here. So let's call this es for this e due to the sphere. That's fine. Es equals es. I thought it was being cool, like, hey, I'm going to call my function e, and this is going to be great. But, okay, so now I'm going to do that. I need to give it the location of my charge, which is RT, the location of my observation location, which is RO. Yes, I double use that name. Yes, that's dangerous. Yes, you shouldn't do it. Yes, I did it anyway. What are you going to do about it? And then Q is going to be DQ. That's it. That's all I need to do. So now down here, I'm going to say print E due to sphere equals ES, and it is a vector, newtons per coulomb. And then I'm going to say EC is the calculate ET, the theoretical one. It's going to be K, which I didn't put. K is in my loop, so I got to put that up here. K is my Coulomb constant. K equals 9E9. So it's going to be K times Q divided by mag RO squared. Right? So mag RO is the vector from the center of the sphere, which happens to be centered on the origin, to where I'm looking at the thing. So that's my R value in that case. And let's print that one too. If this works, I'm going to be super impressed with myself. E theory equals ET newtons per coulomb. And this is going to be a scalar, but we can still compare. I think we're good enough with that. Let's save this thing. E due to sphere, that's fine. I'll say Monte Carlo. Because I'm going to be searching for this at some point, and that's important to have. And I'm going to give you the code. The code is going to be down below. The playlist is going to be down below for all the other stuff, so you can go back and look at the things. It's going to be great. Okay. So, did it work? E due to the sphere is 6.8 times 10 to the 7th, 6.75 times 10 to the 7th. Okay, this is strange. Oh, that's fine. So this is like a really large Y component of the electric field. But that's fine, right? Because it's still much smaller than this, and this one too. And that's only with 1,000 data points. Can I do 10,000? Yes, I can. You know I can, because all I have to do is go up here and go, boom. One more zero. Oh, look at that. I got a nice sphere right there. I get 6.77 times 10 to the 7th. And this is 10 to the 5th, 10 to the 4th. That looks great. Okay. Now let's do, I'm going to put it back 1,000. Let's do a shell. Let's see if the same charge is spread over a shell, then is the electric field the same? Okay, so in this case, and I did a shell before with Monte Carlo to find the moment of inertia of a spherical shell. And I did learn a couple tricks I made a mistake of. But the first thing I need to do is to pick the thickness. In this case, I'm actually going to have all my points between R and R minus dr, where I'm going to pick a dr value. Because I can't have it infinitely thin, right? I can't. So let's just use that. I'm going to say dr equals R divided by, I want to say 100. Let's say 20. Right? If I make it too thin, it's no fun. So now the only thing I need to change is, here I say is RT, I generate that random variable, is it less than R? Well, I want to say also, is it more than R minus dr? Right? So I want it that thin, only in that thin shell. I'm cutting away the things I don't want. So let's say and mag RT is greater than R minus dr. I think that's all I have to do. Let's run it. Find out. That's just 1,000 data points. Not too big of a mistake if it doesn't work. Aha, it worked. See there, you can tell. Can you tell it's hollow? See? And you'll notice here that I still get this a pretty good result. I'm pretty happy with that. And then of course the next thing to do is to make it 1,000 data points instead of just 10,000 instead of 1,000. And there's my thing. I'm really more interested in the art. Okay. And then you see here I get 6.8 times 10 to the 7th, 6.75 times 10 to the 7th. I mean, I think that's pretty good. Oh, these are random though, right? every time I run it's going to get a little bit different. Also, the further away I get, obviously the better my result's going to be, because the further away I get, the more that's actually like a point charge, even though whether it's solid or not. So there you go. That's a great way. I think that's a great way to show students that this actually does work. And this is something the students could do themselves, and they could even use this and plot the electric field as a function of distance. They could do it manually, just by manually changing that R observation location and see how it works. You could try other things. You could try a non-uniform charge distribution. That'd be kind of fun. I'm thinking about how I would do that. But have anything that's spherically symmetric would be the same thing. So there you go. Monte Carlo, vectors, physics, art, electric fields. Code down below, playlist down below. That's it.